Thank you for attending my presentation. I'll talk about vibro-acoustic simulation. This is part of the solutions that we provide. And when we do noise and vibration simulation, we typically characterize the methods depending on the frequency range. So for low frequency, we typically use deterministic methods. So those are methods that are mesh-based, so typically finite element. And they're pretty good at estimating low frequency noise, for example, structure-borne noise. And for higher frequency, we typically use energy-based methods. So they characterize the flow of energy within a car. And it's typically used for airborne noise. Now, when doing this, the methods are very good at the propagation part, but we need to characterize the sources that would need either additional simulation, whether it's a CFD or multi-body, or you would need to have measurements to characterize the sources. But all of this doesn't answer the fundamental question, because our reaction to noise and vibration is subjective. So then if we are seeing multiple curves, which one is the best? Which one do we really have a problem? Do we need to add the cost or weight to a program to tackle a peak or so? And then also how to convince program managers to take on the extra step and extra cost, extra timing to develop countermeasures. And so what I'll be presenting is different applications of how to take these simulation results in a driving simulator for NVH. And so we'll use the NVH simulator, one of the different configuration. I'll be focusing on the noise, but similar process can be applied if you're also looking at vibration feedback. And so with this, then we'll be able to have the subjective feedback, and then we'll add then efficiency to the simulation process, because we'll be able to take into account the final perception by the end user. And so I'll introduce now, so how can we take then the simulation results and bring them in the NVH simulator. And so I'll start with road noise. And for this, I'll use sources here from test. And this is courtesy of HBK. Sources characterized on a single test stand. Sources include the wheel center forces for structure-borne noise and airborne sources at the tire. And then we'll show how we can take them, combine them with a transfer function from a simulation to create sound. And I have a couple of examples that I'll be playing in the presentation. So for structure-borne noise, I mentioned we use a finite element, and the model can include the body. It includes also the acoustic cavity for the interior, and then also porous material, so poroelastic finite element for the treatments in the vehicle. We'd have to include the chassis and tires, because we'll be inputting wheel center forces. And our solvers is a state-of-the-art solver. It's a modern solver that scales very well with CPUs and provides detailed results, not only on the structure, but also on the trim. We can visualize actually how the trim behaves and deforms, and then predict the noise inside the vehicle. For airborne, we use our solver, VA1. It's a best-in-class for statistical energy analysis. What we typically do is divide the vehicle into multiple subsystems. Those can be panels, cavities, and they'll all exchange vibro-acoustic energy. We also model the treatment applied on the panel, and then they can account then for the added damping, the absorption we generate, but also the insertion loss that it creates. And then this is the this is the default method used for airborne noise sensitivity. And with this, then I'll present actually here a results where we've taken then the sources from test, structure-borne transfer function from finite element, airborne transfer function from SEA, and we brought all these results into the NVH simulator. And we'll be driving a car from 40 to 80 kph and then have the audio feedback. It's actually pretty soft, so we have the sounds. They don't seem to go through, but we can make them available. Now, what's important with simulation is that it of course takes time, represents a cost because we have to build model, and it's important to reuse the models as much as possible. And the SEA model can be reused directly for wind noise simulation. The excitation is different. It's coming from CFD. It does require additional processing because we will be applying a pressure distribution, but the pressure can come from the flow itself, but also the noise that is generated by the flow. Those pressures have different scales of magnitude, but the vehicle sensitivity is also different. The glass, for example, can almost be transparent to the sound, but may not let the pressure distribution to the flow generate as much response inside. And so we'll reuse the model. We can do additional post-processing to get the excitation, and then as a result, we can get the sound inside the vehicle. And I have a result actually here that's coming from Bentley. They presented their results at a conference and show the interior sound when driving the vehicle at 100 kph. And what we've done is actually taken the results from their paper and then generated sounds that we can then listen to into the NVH simulator. And that's what we'll be playing now. So this is actually the sound of a Bentley at 100 kph. So we've covered road noise, wind noise, and we'll move on now with powertrain noise. I'll focus on an EV powertrain noise, and for there, the excitation is coming from the electromagnetics and also, of course, the gears. And by performing EM simulation, we can get forces that can be applied to the stator of the electric drivetrain unit, and then with this we can then predict the noise radiation. If needed, we can also include the effect of encapsulation if such treatment is applied, and then we'll get then the sound that is radiated. We can also get the mount forces for structure-borne noise, and then those sources can be combined with the same models that I introduced before to calculate the interior sound. There may need we need to do additional steps to propagate the sound radiated from the EDU to the exterior of the panels before we can use them for SEA, and that may require an additional simulation with a boundary element method. But at the end, so we'll be able to predict the interior sound as perceived by the driver, including both the structure-borne and the airborne contribution. And I will be playing actually here a sound that's applying the process I just described, that includes both structure-borne, airborne, when the vehicle accelerates. Now, of course, here I only included the powertrain sound, so normally, of course, the road noise and wind noise will provide some masking sound, and those tones may not be perceived. And that's what we'll have actually in the next slide, because we'll, I'm sorry, another way actually to evaluate the results is also to look at it from a delta, in terms of a variation. And so an example we wanted to show here is that, and I think Kelby has the demo available, if we include encapsulation around the electric drivetrain unit, we can estimate the radiated sound power and then compare that against the results without the encapsulation. And then with this, we can create an A to B filter. So a filter that corresponds to the effect of the encapsulation. And you can apply this to measurement data or potentially simulation data, and then have an A to B comparison of the effect of adding encapsulation. And that's the next sound that we will play. We'll have the baseline vehicle without encapsulation, and then we'll trigger the filter on and off just to demonstrate the effect of the encapsulation. It may sound like a siren. It's just because then we've been pretty fast at switching on and off the filter. So again, here it's just on the powertrain, and when we switch it on and off. And I think at this point, then we have all the contributions. So road, wind, and powertrain, and we can then assemble them together and put them all together. And that's an example of how we can then use simulation covering all these different attributes and have a purely virtual vehicle that we can then subjectively evaluate. And so I'll be playing this last sound now. In this case, the road and wind were masking the powertrain. Only if we focus, we can hear it at certain for certain RPM range. And with this, I reached the conclusions where we. Oh, I went too fast. So we presented the process developed to oralize CAE simulation results in the NVH simulator. And that allows for realistic evaluation early on, just based on virtual prototypes. And then with this, then we help OEM be better prepared at evaluating the risks of NVH issue, and then prepare for countermeasures and help in the decision process. So all of this is CAE-led, and then hopefully paving the roads to zero prototypes. Thank you.